mighty Jupiter returns this week on Planetary Radio. Welcome. I'm Matt Kaplan of the Planetary Society with more of the human adventure across our solar system and beyond. Scott Bolton is back, the leader of the Juno mission that has spent nearly 5 years orbiting and revealing Jupiter. Has great science to report. Scott is also going to tell us a story about Carl Sagan that you don't want to miss. The fun and fascination continue when Planetary Society Chief Scientist Bruce Betts drops in with another report on the night sky, where there is a lot to marvel at, and you might earn a Planetary Radio t-shirt. Listening to the podcast version of Planetary Radio? If so, you may notice a change. You asked for it. We have delivered. No more commercials. We're on our own now. You may hear about opportunities from the Planetary Society, but that's it. You're welcome. But if you really want to thank us, please leave a review or rating in Apple Podcasts. And share the good news about the solar system and beyond by telling your friends about the show. Thank you. Here are a couple of headlines from the May 28th edition of our weekly newsletter, The Downlink. Pretty certain that a vast ocean of liquid water is under the kilometers of ice that blanket Europa. A new computer model of the Jovian moon now points to underwater volcanoes, much like the ones at the bottom of Earth's seas. And you know what's found surrounding those energy sources on our planet, right? Extraterrestrial tube worms, anyone? Mars Science rover Curiosity has delivered tantalizing but still inconclusive evidence for organic salts on the red planet. If they are there, they could be leftovers from extinct life forms. Or not. Don't you wish we'd get clear data indicating past biology? So does every Mars scientist I know. This has not yet made it into the downlink, but President Joe Biden's budget request includes a big boost for NASA. You can bet this will come up when Casey Dreyer and I bring you the June Space Policy Edition of Planetary Radio. Dr. Scott Bolton is Associate Vice President of the Space Science and Engineering Division at the Southwest Research Institute in San Antonio, Texas. He is also Principal Investigator for NASA's Juno mission to Jupiter. He doesn't just oversee Juno. Scott led concept development for the mission's microwave radiometer experiment that peers deep below the swirling clouds of our solar neighborhood's biggest planet. He spent 24 years at NASA's Jet Propulsion Lab before joining SWRI, but he has never ended his deep collaboration with JPL, where for 24 years he worked on missions including Magellan, Galileo, Cassini, and, as you'll hear if you stay for his delightful story about Carl Sagan, even the Voyager Grand Tour missions. He received Smithsonian Magazine's American Ingenuity Award in 2018. Scott Bolton, welcome back to Planetary Radio, and congratulations on this extension of the Juno mission. You were about to celebrate your 5th anniversary at Jupiter, 10th anniversary of launch. Now we can congratulate you on the extension to September of 2025. Richly deserved.
Thanks so much. It was really exciting to hear about that extension. You know, just putting it together was just an amazing experience because we were looking at the orbit, and of course we had all these discoveries that we wanted to address and do more of and get closer to the northern hemisphere. And then we realized that we had the opportunity to go close to the satellites and the rings, and the whole mission opened up. I mean, it was just like, we're really a full system explorer. It's awesome.
Did you have any hope that things would go so well that you'd be able to turn away from Jupiter and examine Europa and some of the other moons and those rings?
Exit right.
We knew we had the capability when we were launching it originally, but we weren't getting very close. In fact, we were purposely staying far away, right? We didn't want to disturb our orbit, and if you get too close to those, the orbit changes. And so we did some distant observations during the prime mission of both the rings and the satellites, right? We got some interesting images of Ganymede and Io, but I don't think, I mean, I'd love to take credit, but I did not have the vision that we would actually completely transform the mission like this. And a lot of it is, we're basically built like an armored tank. And of course we were nervous and worried about the radiation environment and eventually hurting the spacecraft. And we really haven't seen any hints of any damage yet. And everything's working perfectly. And that's really what opened the door. Yes, I had a hope that maybe the radiation wouldn't get to us and we just keep going around and we do more and more Jupiter. But I did not realize that we would have the opportunity to fly by really close to the satellites. And of course, part of that was because we stayed in the orbit that we originally went into. We were in this. Originally, the plan was to go into this big orbit that was 53 days long and then shrink it down to like an 11 or 14-day orbit. That would have eliminated this possibility. And of course, we wanted to do that. And we saw some hints of in the rocket system, in the fuel system, that said there was a little bit of a risk there. And we said, well, the whole mission will work with this bigger orbit. Let's just leave it alone. That opened the door for this extension. Sometimes things happen and you make lemons.
I was going to ask you if staying in this longer orbit had proven in some way to be a blessing in disguise. Well, obviously it has been, but what about for your observations of Jupiter? Have there been other advantages to staying in this orbit?
Absolutely. Before we got there, we didn't know that we're going to have polar cyclones covering both poles. When that was discovered, not only are they amazingly beautiful and intriguing, but it's not clear how they're made or how long they are able to be maintained, and does the configuration change. Having this longer orbit has allowed us to monitor those over the years, and we've seen things that look like they were going to change there, where a new one was going to come in and it sort of opened up, another cyclone had formed and space started to open up between two, and we thought, wow, there's going to be a new configuration. We're watching one get made. And then we went around again, and then by the time we went around again, the new one had been booted out. Evidently, it's a very exclusive club.
They really do. It's like the almost permanent cyclones kick out newcomers, blackball them.
Maybe. I'm not sure what it is. I mean, we're watching them evolve. And one of the exciting things about the extended mission is we have this instrument, the microwave radiometer, that actually gets to see below the cloud tops and sort of see the roots of these storms. In the original mission, we're not close enough to the poles. We're close to the low latitudes, but when you go over the poles, we're at a larger distance away from the planet. And so these microwave instruments don't resolve the storm itself. It sort of mixes it with the surroundings. But during the extended mission, we get much closer to the northern hemisphere and the North Pole. And so at some point, we'll actually get the beam or the resolution of the microwave instrument to be smaller than the cyclone that we're looking at. And so then we'll be able to compare the roots of that with other cyclones and other vortex storms across Jupiter. We'll learn about what's underneath them, which will be fascinating. Not to mention, I mean, you already are going to be able to keep monitoring them and learn about how they're structured, how they are made. It's very exciting new science, all based on an unexpected discovery.
Seems to be how it works. Often enough. Certainly glad to hear it's happened this time as well. We're going to probably come back to those views of the poles as I ask you about some of the recent science.
Turn left.
I just wonderful news that you're not seeing the effects of the radiation that, as you said, you feared so much. This must be causing enormous sighs of relief among your colleagues at JPL who are starting to build the Europa Clipper, which is going to face the same challenges.
Absolutely. Of course, they have a different orbit, so the radiation that they'll see is a little bit different, but we're in close touch with them, giving them input about how we see the radiation. If we see, the lack of us seeing effects from it. We don't see much impact on the solar cells. You also kind of thought that those might be great, and so all of this was sort of an experiment. They're modeled after us. They have a bulb, they have the solar cell. It's really good news to them. And then on top of that, because of the orbit, we're going to actually cross through the region that they actually are going to orbit. Before, we've been much closer to Jupiter than they would get, so if we measure the radiation, it doesn't really help them that much because we're in a different place. But both Clipper and JUICE, the European mission that goes to Ganymede, we're looking at the radiation environment and measuring it. We have very sophisticated fields and particles instruments, so we're going to be able to really characterize the environment for both missions around Ganymede and around Europa. And of course, we'll share that with them and they can update their models. And of course, we'll get observations of the moons themselves, which will kind of complement their measurements.
JUICE, of course, the Jupiter Icy Moons Explorer, as you said, from the European Space Agency. Let's go on to some of your own science that is still underway, of course. I want to note first, you finished the 33rd pass last April. We must be getting ready for number 34.
We are. I think it's June 8th. And on the 33rd one, we completed our goal for the magnetic map. What we were trying to do was pass by very close to Jupiter at different magnetic longitudes in order to make a map. So the map itself is divided into 32 sections. We had 2 spare orbits in case something went wrong. We were able to make up a longitude. We used up 1 spare back when we were going to change our orbit and fire the engines, and we didn't do it. And we never used up the 2nd spare. So we actually completed that map on the last orbit, which was a kind of a celebration that we had finished that. Of course, the next one still gets us great data, and we're still going to go by, and we're getting incredible images now. As you get closer and closer to the poles, the geometry's changing, and you see all these things. So we're very excited about, one, completing the 33rd orbit, science orbit, and still not having any radiation effects. We're getting great measurements. And on the 34th one, even though we're still in our primary mission, we've already adopted the orbit because we no longer have to go into Jupiter. Originally, the planetary protection would say if you were ending the mission, you should then fire the thrusters and enter into Jupiter in order to protect yourself from crashing into Europa.
As Cassini did.
That's right. And we're not going to do that now. Instead, we're going to fly close to Ganymede on June 7th.
Wow. Will you, I know you've got instruments as well, but will JunoCam be able to get some shots as you fly by?
Absolutely. Now, of course, we're different than Cassini and Galileo. We don't have a big scan platform. We don't have a telephoto lens or a wide angle. We have JunoCam, which produces incredible imagery for Jupiter, but that's what it's. When we go by Ganymede, we will get Voyager, Galileo level resolution images of that surface. I expect it to be spectacular. But we won't get the faraway shot that you normally would get because the spacecraft's pointing toward the Earth. Ganymede's literally not in the field of view. But we do get close-up pictures on June 7th, which will be really exciting. And we get a lot of other science, right? We go through the magnetosphere and we fly by in a snapshot coming from the south going toward the north, so we see something that nobody's really seen before. We'll look at the effects of sputtering onto the moon. We'll go by pretty close, 1,000 kilometers away from the moon.
Wow.
So it's closer than the Galileo spacecraft really did. And we'll get spectacular science. We'll also make a map with a microwave radiometer of the ice. And nobody's ever seen that before. The closest thing we have are radar and VLA type observations of Ganymede from far away a long time ago, but they're very low resolution. We're going to make a map at 6 frequencies and basically interrogate the top 5 or 10 kilometers of the ice.
Absolutely thrilling. I will settle for close-ups from JunoCam.
We even do a radio occultation.
Oh, no kidding.
So we'll look at the ionosphere.
And that, of course, remains, to me, still one of the most amazing things that spacecraft are able to do. And to be able to do it from, as far away as Jupiter and even further as Cassini did at Saturn, just blows me away. Let's talk about what's happening at those poles. I did read a little bit about the work that's being done on those auroral storms. It's almost romantic, auroral storms at dawn. There is some beautiful, beautiful images and actually a sort of a low frame rate video, I guess, on the Juno site that we will link to, along with a lot of other things that we'll be talking about on this week's show page at planetary.org/radio. Can you tell us about these beautiful auroras that are so much like what we see at the poles of our own planet and still quite different?
Yeah, they're spectacular, and we're getting great images both in the ultraviolet and the infrared. And of course, we have the particle instruments, and the plasma wave, and the magnetic field. So when we go over them, we're really looking to match the flux of particles that are going into the atmosphere with the emission that we see in the aurora. So you have this beautiful structure. You see an oval, kind of like what we see at the Earth, but then you see these umbilical cords or whatever, these things that are associated with the moons, right? So they're linking, and they're making their own spots in the aurora, and we're getting close up. And one of the exciting things is as we go closer and closer over the course of the primary mission and into the extended mission, we're lowering our altitude over those auroral regions. We were surprised. Even though we thought we were close enough, the amount of light coming out of the aurora did not match the particles that were precipitating into the atmosphere as far as acceleration goes. And so we believe that it must be below us. And fortuitously, we're going to keep measuring closer and closer. And eventually we're going to probably be able to see that or explore that region. And that's a little bit different than the Earth. There are significant differences between the Earth's aurora. We thought it might be between Saturn, and it seems to be its own beast, but it's quite exciting. We also see the effects of the aurora in the microwave, which was sort of a serendipitous thing. We can actually measure and see it reflecting into the microwave instrument. We are getting to the point in the extended mission where we'll be going over the night side, so we would actually be able to make visible light images of that as well. So there's a lot of incredible stuff with the aurora, and they're just naturally beautiful. I mean, if you ever get a chance to see the Earths and go up to Alaska or anywhere in the north, you get to see those during winter. It's dark. It's just dancing lights. I can only imagine what it must be like to hang out in Jupiter's atmosphere and what it must look like looking the other way.
That's a view I would love to see. It sounds like you would too. Yeah, I did get to cross off our own aurora on my bucket list not too long ago. It was spectacular. I recommend it, everybody. When you talk about these threads of energy between the auroras at the poles of Jupiter stretching out to the moons, the Galilean moons, can it be thought of almost like those fun plasma balls you can get at knick-knack stores, and you touch it and there's a string of energy, glowing plasma between your finger and the center of that evacuated globe?
Yeah, it's a little bit like that. I mean, what's happening is Jupiter has a gigantic magnetic field and magnetosphere, but the magnetic field lines come out of the poles, right, and go in to the other pole. They go out pretty far away from Jupiter, and so the moons are orbiting there. When the moons orbit, or the magnetic field is actually going around at about 10 hours, and the moons are going around, Io's about a day and 3/4, Europa's a little bit longer, but they're going around in days, let's say. So what happens is the field spins past them. When the field line connects to the moon, they can transfer particles literally back and forth, and currents. And those currents and things like that can accelerate particles right into the atmosphere. It works a little bit the same way at the Earth as well, although we have a lot of effects from the solar wind. Jupiter's got a lot of energy internally to its magnetosphere because it's spinning so rapidly around. It's like an engine. What's interesting is you have in the moons of Jupiter, you have Io, which is spewing out volcanoes. You have Europa, which may be outgassing things like water, right, and maybe geysers.
Fingers crossed.
And then you have Ganymede, which has its own magnetosphere and magnetic field. So all of those are interacting a little bit different from each other. And Ganymede essentially has its own aurora, and we'll look at that. We've seen it already on the 29th orbit. We looked in the UV and saw the glow coming from that. And we'll get a little bit closer and get higher resolution in the next few months.
Mind-boggling. Let's talk about lightning, specifically shallow lightning and mush balls, which my colleague at the Planetary Society wrote a really good article about on May 4th. My colleague Ray Paletta. Also fascinating, and accompanied on the website by this knockout animation, which a lot of people contributed to. Give credit to. Well, I'll let you give credit to. You know the one I'm talking about, right?
I do. Of course, I'm always afraid I'm going to leave out a name. I saw that article that your colleague wrote. It was fantastic.
Oh, good. I'll let her know. Thank you.
In fact, I spoke with her a little bit about it as one of her sources of material that she talked about. It's a fascinating topic. The link between the lightning and mush balls is fascinating by itself, because they were independent efforts. We were working on trying to explain how the ammonia and the atmosphere could be changing so deep in Jupiter, way below where you would see the condensation. Once ammonia reaches a temperature where it's all evaporates, it no longer condenses into liquid, or it no longer has ice, then most theories have it say that, and most people had assumed that once I get below that, I'm kind of below the weather layer, it's just going to mix up, it's a gas. I'm not going to have the liquid anymore, it's too warm. And yet we see variability in ammonia really deep, and we're trying to figure out how can that happen? What's happening in Jupiter? We were playing with that, and there were people trying to play around with it at first with rain, and the rain couldn't do it enough, because the rain would only go down until it evaporated, and you couldn't really mix it in very well. And I said, I thought, well, maybe if we use solids, because I live in Texas and you got hail all over the place. And I'm thinking, it's very warm, and I see a piece of ice land on the ground and bounce around. In fact, it'll break a hole in my table or knock out a roof or dent your car. So it's a very real thing here. Thought, well, if you made that, it might go down further. And so we started looking at that, and the scientist that was leading that effort was Tristan Guillot from France. Very brilliant guy, and he put together the whole story and had this idea of how you could actually create this. And around the same time that we were presenting that for the first time, Heidi Becker, who leads our Stellar Reference Unit, which is the SRU, it's basically a low light camera that we use to navigate, but she uses also to do radiation monitoring. She had taken some pictures of Jupiter and detected lightning. And because we were closer and she had higher resolution than any, lightning imager had before, she detected small lightning. It was smaller than what anybody had seen before. And lightning is just assumed that they calculate the depth of the lightning based on the size of the flash. How big of an image of the light do you see? And you assume it starts small somewhere in the cloud where lightning happens, and then it just grows right as it goes out, because light, like from a flashlight, goes out spherically. And so you can see how big it is on the cloud top, or wherever you are able to see it, and then you can propagate downward and say, well, this is where it is. So most of the lightning that Voyager had seen linked to the water clouds. It wasn't a big surprise. That's where we expected it to happen. Heidi's detection were smaller, and it was above where the water clouds were, and in fact it was above where liquid water could exist and had to be frozen. There are theories that suggest that in order to get lightning you need 3 phases. You need the liquid, the ice, and the gas to get the charges right. You can make lightning without it, but not at these levels of energy. So I'm looking at that and we're realizing, okay, it must be higher up. So what's happening? There's a liquid further up. It must be ammonia is mixing with the water ice and acting like an antifreeze, and literally creating a new solution, a little bit like Windex, or the old Windex. Yeah. The new Windex isn't ammonia and water, but the old one was. It's an antifreeze. And so then I went over, I said, I think this might be linked to the mush balls. It's another piece of that confirmation for a consistent story. And indeed, in the mush ball theory, you had ice, water ice, shooting up in narrow jets and hitting the ammonia. And the ammonia is melting it, creating sort of a slushy liquid that then gets made into hail and falls back down. The mush ball theory was saying that you needed big that, but we didn't think that you'd have lightning generating from these, that there'd be some other liquid cloud or something. But then when they put in the mush ball theory and put in a factor for the storm state more or less reproduced our data pretty well. And so these two theories came out around the same time. Heidi put together her paper on the shallow lightning. We call it shallow because it's higher up in the atmosphere, right? And put together this video to try to explain it to people.
Don't you love it when the model fits the data?
Yep, it's amazing. Often you get more questions when you start to do that, and we still have questions. We'll now be able to make more and more observations also from the night side, but we'll get statistics on the shallow lightning and how small it is.
Go straight
and
on.
That will fold into the theory for mush balls. We also notice when we look at lightning, because we look at it in different ways. We can see it with the plasma wave instrument, we can see lightning with the microwave instrument, and we can see it with the cameras. We've noticed that it's more prominent in the northern hemisphere than the southern for some reason. It's one of the asymmetries that we've seen. And on top of that, it's at fairly mid-high latitudes. There's more of it. So that's right where we're going with the extended mission. It's going to be just, it's a beautiful connection.
Stay with us. Scott Bolton has more fresh science from Jupiter and one of the best Carl Sagan stories you'll ever hear.
Bill Nye, the planetary guy here. The threat of a deadly asteroid impact is real. The answer to preventing it? Science. And you, as a Planetary Society supporter, you're part of our mission to save humankind from the only large-scale natural disaster that could, one day, be prevented. I'm talking about potentially dangerous asteroids and comets. We call them near-Earth objects, or NEOs. The Planetary Society supports dedicated NEO finders and trackers through our Shoemaker Near-Earth Objects grant program. We're getting ready to award our next round of grants. We anticipate a stack of worthy requests from talented astronomers around the world. You can become part of this mission with a gift in any amount. Visit planetary.org/NEO, and when you give today, your contribution will be matched up to $25,000, thanks to a Society member who cares deeply about planetary defense. Together, we can defend Earth. Join the search at planetary.org/NEO today. We're just trying to save the world.
I mentioned that video. I only wish we could show it. It's one of those times when I regret this being merely an audio podcast radio show. But we can at least share a bit of the music that backs this fairly short video, although there's a longer clip as well, a flyover of Jupiter. And I do want to give some credit to some of the people behind all of this, beginning with that composer. I think we'll use it at the very end of today's show. And most of you out there probably have heard of the person behind it, Vangelis. You got him to compose some music for you, your mission, and Jupiter.
Absolutely. Well, I've been friends and a colleague of Vangelis for over 25 years. I mean, way before Juno came along. We were already doing stuff together because I kind of have another path that mixes science and art and music together. And so we were friendly, and he had already done things like he put together, he worked with Carl Sagan on Cosmos and
sure.
done other music like that. So it was a natural for him, but we've stayed friendly. And so, I mean, I literally call him up and say, hey, we've got this video, what do you think? He'll say, send it on, and the next day we'll put the music out and we'll play around with it. The music's spectacular. It's all, he just creates it. He's inspired by what we're sending him.
I'd be surprised if he wasn't. And apologies to Vangelis. I guess a lot of people make that mispronunciation.
Actually, he's living in France, and the way you pronounce it is Vangelis there, or Vangelis. So everybody pronounces it differently. I simply pronounce it the way it's introduced to me in Greek, when I would visit him in Greece originally. And it's actually a very common name in Greece.
Oh.
And when I went to meet him for the first time, like 3 or 4 people in the house all named Vangelis. It was very confusing.
I do want to give credit to a couple of other people who contributed to that.
Koji,
Koji,
and Heidi Becker, right?
And Kevin Gill.
And Kevin Gill, absolutely.
So Koji did this gorgeous animation But some of it was based on images which pop up all over the place. Images largely taken from JunoCam that have been processed by this so-called amateur, Kevin Gill, who happens to be a computer software guy at JPL, but does this on the side. And I have seen other work by Kevin that reveals just how amazingly powerful JunoCam seems to be.
Absolutely. Kevin is gifted and has a great eye and is obviously very technically competent, and he's made some incredible contributions to us. We take all the data, the JunoCam data, and we post it for citizen scientists to play around with. Some of them are technical backgrounds, like Kevin, although he isn't an imaging analyst. He does that for fun. And that's what's beautiful about the whole JunoCam experiences is you're giving people that from all walks of life a chance to go play around and make images. What we post is not an image at all because we're a spinner. It doesn't look like a picture at all. You have to actually figure out how to create it. There's a whole bunch of people like Kevin. Kevin's one of the best, but we have a number of people. Gerald Eistat, there's a whole list of them. We literally have thousands of people playing around with the images. Some of them are artists, and they're making an image that doesn't necessarily look like Jupiter. It's their image of it or vision, and the colors are stretched or the whole image has changed. I've got ones that people have sent me that look like a heart for Valentine's Day, or it looks like a cat. Or has astronauts put into it, or spacecraft put into it. They literally have poetic license to do what they want. And some of them are made also scientifically correct or with science in mind, and we literally use them for that. We've invited people from those citizen scientists to be on papers because they're doing science.
Power of citizen science. Let me bring up one other example of Kevin Gill's work, which was recently published on the website. There are two different views. There's one from 2020 and one from just last April. And it has to do with this thing called Clyde's spot, discovered by yet another amateur, this time an amateur astronomer, Clyde Foster in South Africa. And I saw both of these were also processed by Kevin. And it is absolutely fascinating to see a year and a half apart, something like that, the development of this storm on Jupiter.
Yeah, it was amazing. We have a large effort to coordinate amateur and professional ground-based, earth-based astronomers to help us. They literally, they're watching Jupiter when we're not able to see it, or they're seeing it from a different angle, and it's been a really successful effort. It's led and coordinated by one of our co-investigators who, I asked to do this because he himself was a great astronomer named Glenn Orton, who's at JPL. So Clyde was one of the people that was, helping us and doing these things. And he sent out a notice saying, I discovered this spot. It was kind of near the Great Red Spot, but it was clearly a new storm that nobody had seen. And we happened to be flying right over it a couple days later and got a close-up view of it. And Kevin and others all analyzed that. It was a beautiful storm. It had this shape. And then about a year later, we went over the same thing, and it had changed dramatically, right? In its shape and its contour. It's got all these folded filaments that are sort of folding in on each other, and it's still beautiful, but in a different way. And so we put together a press release that showed both, then and now. And we involved Clyde again, and of course Kevin was involved. And it's amazing that we're lucky to be there, that we can get close-ups and watch how these things evolve. The Great Red Spot itself is changing while we're there. It's shrinking and things are changing, and you're seeing how that happens. But Clyde's spot was a spectacular example of the advantage of having Juno there, seeing how Jupiter really works.
And we'll include a link at planetary.org/radio. Great Red Spot, sure. What's up with this cousin of the Great Red Spot, the Great Blue Spot?
Yeah, so that's actually a magnetic feature. So when we map out the magnetic field, we saw this feature that was almost serving like a pole. I mean, it had a lot of. So we called it the Great Blue Spot. It's near the Great Red Spot, but in the sense that it's just a little bit south. But of course, the Great Blue Spot moves around with Jupiter's rotation. The magnetic field basically defines Jupiter's spin. So it's moving around the whole planet every 10 hours or so. So it's tied to a specific magnetic longitude, if you will. The Great Red Spot is literally blowing in the wind. And so it moves with respect to the Great Blue Spot. It doesn't stay in the same place relative to it. But one of the more amazing things about the Great Blue Spot is as we got closer and closer and got enough passes that went over it, we mapped it out magnetically. And you could see that in the north, it was sort of treading between two jet streams, one going to the right and one going to the left. Or one going east, one going west. And you could see that as you got better resolution of that Great Blue Spot, that the one that was tied to the jet stream that was moving easterly was distorting the magnetic spot in that direction. It was being sheared. And the one on the bottom, which was tied to a jet stream going the other direction, was being sheared the other way. When we discovered that and realized that it was really the deep atmosphere was messing with the magnetic field.
Which just sounds crazy. How could wind be changing the magnetic field? Well, you have a theory about that, right? Or a hypothesis?
That's right. Well, what you need is the wind to be penetrating down deep enough into Jupiter where the atmosphere becomes conductive. So eventually I go down and the atmosphere has enough conductivity. In fact, at some point, that's where the magnetic field is getting generated, but probably deeper than we're seeing. And this is deeper than what we can see with the microwave radiometer. But we'd already detected that the zonal jets go down at least as far as we can see with the microwave, and the gravity field was able to see that the asymmetry of the zones and belt structure sort of was mirrored in the gravity field, and we estimated 3,000 to 4,000 kilometers. And below that, maybe Jupiter was rotating around as a solid. Above that, it had these cylinders. But somewhere, you get into a region where it's conductive, where there's enough charged particles in the atmosphere to literally conduct electricity, electromagnetic fields, and the winds must be penetrating down at least that deep.
What a world! This captures most of the most recent stuff that I've been able to discover coming out of your data, these amazing images. What have I missed before we go on to a couple of other less Jupiter-related questions I have for you?
Well, there's the puzzle of the dilute core, which I think we've talked a little bit about before.
Yes, we have.
But we continue to model that. It's very puzzling. The theorists are a little bit behind the data in the sense that we see the evidence in the gravity field that the core must be fairly large and dilute without sharp boundaries. We were originally set out to figure out whether there was a compact core of heavy elements in the center or none. And it was going to help us understand how Jupiter formed. Did you form it by creating a bunch of asteroids or rocky things and then have the atmosphere collapse on top of it? And instead, we see this diluted core, sort of fuzzy, and it's quite large. And it's not clear how you make a Jupiter like that. It's not clear that you could start with a compact core and have it evolve to that. And so it's kind of a puzzle. One of the theories is that maybe Jupiter was hit pretty hard early on, enough to shake up its core a bit. And to me, I don't find that hard to believe, because I think things are probably hit often throughout the history of our solar system. Certainly we think that happened with the Earth and Moon, but hitting Jupiter, and you've got to hit it with a big enough piece that you've affected its core, and Jupiter's pretty big. So it had to get hit pretty hard to do something to it. And recently people have started looking at Saturn and doing seismology with the rings, and there's a paper out there that suggests it might also have a dilute core. And so maybe we're learning something about giant planets in general. They're not like we think.
Go straight on.
I think a theme of Jupiter, or a theme of Juno, is rewriting the book on Jupiter, because when you get up close, the deep atmosphere didn't work like we thought. The poles didn't work the way we thought. The aurora doesn't work the way we thought. The magnetic field doesn't seem to work. I mean, so we kind of had to eat some humble pie and say, okay, from far away it looks like one thing, and when you get up close, those theories don't always hold up. So the dilute core, I think, is still a field of active research. Even though we suggested it a while ago, it's a new result to this day, and there are models still going on trying to match it out and understand the equation of state. We're right at the edge of our understanding of even how hydrogen behaves under great pressure and temperature. We're bumping into our knowledge of fundamental physics, basically.
Ain't science great? And the only thing that would have surprised me would be if there hadn't been any surprises revealed by Juno. Let's come back to Earth as we go into the home stretch here. You up front is Associate Vice President, SWRI, the Southwest Research Institute, which is a name that comes up pretty frequently on this program and elsewhere. You head that division, the Space Science and Engineering Division. Can you tell us a little bit about SWRI and what your division does?
Absolutely. It's space science and engineering. We do a lot of both, all related to space exploration. Besides Juno, I mean, obviously there's a whole team of scientists working on different fields. They built a couple of instruments that were on Juno, the plasma instrument, which we call JADE, and the ultraviolet instrument, which is called EVS, were built at in San Antonio. They have a copy of the ultraviolet instrument on the ESA mission JUICE that goes to Ganymede. They have another copy of it also on the Europa Clipper. I say they're copies, they're not exact copies, but they're similar, sort of the next evolution of the instrument. They also built the mass spectrometer on Clipper, one of the most important instruments that are going to measure the composition of Europa and see how the organics and the potentials for life there. So they do quite a bit of science. They also run the science team for the magnetosphere multiscale instrument mission called MMS, which is orbiting the Earth. A lot of our work studies the magnetosphere and the aurora of the Earth. They've done quite a few missions and contributed to different things that orbit the Earth, study the heliosphere, the magnetosphere of the Earth. And then we have another office in Boulder, and of course that's where New Horizons, the mission that went to Pluto, is led out of. They also do some Earth orbiting stuff. There's a mission being developed there called Punch. That's fantastic. And in fact, we also did some of the first small space where we have a mission that studies the hurricanes. And we have a constellation of very tiny spacecraft that are all invented and built in one of our engineering divisions. So it's a very broad organization and services NASA in a lot of different ways.
Busy place. I want to turn to your earliest days at the Jet Propulsion Lab. We mentioned up front that you had years there, of course, before going to SWRI. And of course, you still work closely with JPL on the Juno mission. But I want to take you back to the very beginning and a story that we have tried to tell in the past on this show, which is going to be as delightful to a lot of folks out there who are Carl Sagan fans as it was to me when you first told it to me, and I think you first told it to me sitting in a lunchroom at JPL. Tell us about this interaction that you had as a very young scientist with Carl.
Yeah, that's a fond memory of mine. So I, with an aerospace engineering degree out of University of Michigan, and I went to JPL in the summer of 1980. I was attracted there because somebody came and gave a talk at the University of Michigan about Voyager. And I wanted to go to another star, and I went, well, that place is going the furthest. I got to go there. So I went to work there, and just in time to see Voyager going past Saturn. I might have missed the first one, but I got the time for the second one. I don't remember the exact time, but it was very quick. And of course, the place was on fire with press, right? I mean, I would drive in and trucks with antennas and things all lined up outside. It was a real heyday for the press and the media, and I was amazed at what was going on. And you go in the middle of the night, you go into the cafeteria and watch the pictures of Saturn. They would publish what picture was coming down when, and I would go in the middle of the night with friends, and we would just watch them, and it was amazing. And of course, I wanted pictures. I wanted to get my own versions of the pictures, and I found out where the laboratory was to actually make the photos, and I would hang out there, and I would get some that way. And even though there was always a shortage of photos because almost everything they were making went to the press.
This is pre-digital, of course. So
it was all it wasn't pre-digital, but it was the early days of the internet, and so you didn't have the same thing. I mean, when I first got there, I was still programming in Fortran, and you didn't really have email. Starting to make these networks, and so everything was hard copy, and certainly all media people weren't using computers yet. I'm old, right? There were no cell phones back then. I wasn't very far from typing in on cards in order to run a program, and the computers were big and heavy. The calculators were big and heavy.
Yeah, I remember.
This is something my kids have no concept of. And so anyway, I'm there and I'm trying to get these pictures, and I'm sneaking around, and it was hard to get them. And eventually I found where the media offices were, which were in the administration building, almost up on the top floor, one of the top higher floors. And they were saturated. They would have boxes and boxes of these photos and lithographs that they would hand out to the press and media. So I would hang out there hoping I could pick up a scrap or something that tore and nobody wanted or got folded or whatever it was. But I didn't always follow the rules completely. And so I found myself in there in the middle of the night one night. The lights were out and the door was unlocked, and I walked in, and I'm looking around in the dark because there's guards around and I didn't want to get in trouble, but I thought, well, maybe I'll find some photos that nobody wants or something laying on somebody's desk. I'll get a souvenir and I'm going to be able to see the pictures. Even if I didn't take it, I just wanted to look at them, right? And there's no phone. I've got an old-fashioned flashlight, right? And I'm looking around trying to stay quiet. I hear a noise out in the outer office. I'm already in the inner ones. And I'm like, oh no, I'm going to be in trouble. So I hide behind a desk and I turn off the light and I'm waiting. And I hear somebody shuffling around. Also, no lights are on. They're doing it with a flashlight too. So eventually I get enough confidence that I'm thinking, this person's not supposed to be here either, or they would just turn on the light. They're not going to get me in any trouble. And maybe they know where something is, So I finally get enough courage to step up. Oh, you must be looking for pictures too. And the voice comes back and said, yes, I am, but it wasn't an ordinary voice. Right away, I heard that it was Carl Sagan, and I knew, and I when I heard that voice, right, I was like, oh my gosh. So I said, are you Carl Sagan? We're still in the dark, right? And he said, yes. And I said,
a new
oh
route.
my God, I'm a huge fan of yours. What are you doing here? And he goes, I'm looking for pictures. I said, but you can get anything you want. And he goes, no, I can't. They all go to the press, and I have all these interviews in the morning, and I can't get them. I'm trying to prepare. And he goes, and they won't give them to me. And I said, are you kidding? I said, well, here's some I found. And he's looking through them, and he goes, well, here's some I found. And we started comparing notes and trading pictures. And I said, I can't believe you're up here in the middle of the night. And he goes, yeah. And he said, so tell me about yourself. I said, well, I'm an aerospace engineer, but I'm starting to go back to school. I'm going to study physics at Caltech and be a scientist. I started working on Halley Comet missions. And he said, oh, that's what you should do. He goes, go back to school as soon as you can, get as much degree as you can as early as possible. He goes, you're doing the right thing here. This is great. It was an introduction kind of in a funny way, but we stayed friends after that. It was such a bizarre introduction. He stayed in contact with me, checking on me. And when I went to take classes and I was at Caltech for a while, then I was thinking, okay, I think the advisor I was working with moved and left, and I said, I'm thinking of going up to Berkeley, and I talked to him about it, and he goes, oh yeah, that's good, you should go up to Berkeley, they're fine. Caltech's great too, you can be at either one. And in fact, he even said, what about Cornell, have you thought about that? And I said, I'm going to stay close to JPL so I can go back and forth. But he stayed in touch with me, and we traded, science papers and different things. He was a great advisor and incredible friend. The funny thing was later I started working with Vangelis, who had worked with Sagan, and the whole time I was talking to Sagan, Vangelis never came up. It was just a coincidence that we both ended up there. It's a great story, because it was Carl Sagan, and who would think you would meet him in the dark?
With flashlights. Scott, if that isn't the best Carl Sagan story ever, it's right up there. I have to think that Carl would be very to see how, rather than forcing people to skulk around with flashlights in the dark, you are making data and images available of this magnificent planet for all to see and work with. And I'm so glad that it's going to continue for many more years, at least until September of 2025.
Thank you very much. Yeah, that's it. I want to share it with everybody.
Thank you, Scott. It's always a delight to talk, and I look forward to checking in again as Juno continues to whirl around that big world.
Thank you. It's always a pleasure to chat with you.
Same here. Scott Bolton is a Southwest Research Institute Associate Vice President and Principal Investigator for the Juno mission. Time for What's Up on Planetary Radio. Here is Chief Scientist of the Planetary Society, Bruce Betts. Welcome.
Hey, Matt. Good to hear you.
I have a message that you'll like. It came from Brandon Gaskins. He says, I just moved across the country from Mount Rainier to Acadia National Park area in Maine. Listening to you and Bruce definitely made it an easier drive.
Oh, how nice. That sounds like a lovely place.
Yeah, a road trip. He took us across the country with him. But you know what's even better? I'm going to be visiting Maine and Acadia National Park for the first time in October. I'll see you there, Brandon, because I'm sure we're bound to run into each other.
Do you just plan your trips based upon listeners' emails?
Just now. Just in the last few minutes, yes.
I've moved to the seventh circle of hell. Oh, I'd love to vacation there.
I hear the air conditioning is out most of the time, but otherwise it's okay. Hey, what's up?
So anyway, as I attempt to recenter my brain, we've got good stuff to look at in the evening sky over in the west. Venus getting higher and higher. It's still low, so you want to look soon after sunset. Low in the west as usual, super bright. And Venus is, as it gets higher, we'll be hanging out next to the moon, the crescent moon, on June 11th. And then on the 12th, the crescent moon will be between Venus and the much dimmer reddish Mars. And on the 13th, the crescent moon hanging out next to Mars. Mars has a fun lineup going on, looking reddish and like a kind of bright star. It will actually, on June 7th, be in a nice line with Castor and Pollux, the twin stars of Gemini, all about the same brightness, Mars much redder. We've also got, for some of you in the world, an annular solar eclipse, where the moon does not completely cover the sun, but if you're in the right place, you get the outline of the sun around it. Please use safety glasses. It is never safe to look at an annular eclipse without them. That will be on the 10th of June, and visible from, at least partial eclipse will be visible from central and eastern portions of Canada, Greenland, Russia, and northeastern U.S. and Europe, and Europe's also going to get some partial. The actual annular eclipse is pretty limited to northern Canada, across Greenland and Russia. That's June 10th. Check it out. Live there. I'm sure there'll be some lovely webcasts.
Have fun, folks. Wear that protection.
Pre-dawn, still got Jupiter and Saturn. Jupiter looking really bright. Saturn in the ocean. And they're hanging out over in the southeast. We move on to This Week in Space History. 50 years ago, Surveyor 1 was launched, the first soft landing on the moon by the U.S., the robotic precursors to the Apollo landings later on. And in 2003, Mars Express launched on its way to Mars, and it's still working, still doing great for the European Space Agency.
Just amazing longevity. And, it sounds like from what Scott Bolton was telling us, Juno may have the same kind of luck, at least until it runs out of gas.
We'll have a related fact in just right now? Random space fact. So Juno, which you may have heard of moments ago, has big giant solar arrays, which you may have heard about a little bit recently. The active solar cell area of the solar arrays is just slightly under 50 square meters. That is, for the completely Planetary Society obsessed among you, 55% larger than LightSail 2's solar sail, the sail at 32 square meters. It's just the solar cells are bigger for Juno. Now, Juno is over 300 times more massive, and out at Jupiter, where there's 1/25-ish as much sunlight, and so it's not doing a lot of sailing. That gives you a comparison. They're big solar arrays.
I love it. I love all of that. That's fantastic. And they may just keep spinning around up there and generating power for a long time to come. So, yeah, good stuff.
Good stuff. Well, let's continue the good stuff and go on to the trivia question. I asked you, what is the most massive star within 10 light years of Earth?
Our winner, first time I think, is Cody Roxwald. Cody Roxwald in Florida said that it's Sirius A, Alpha Canis Majoris A, the dog star, a little bit more than two. He adds, "Thank you for making me learn more about the known universe. Can't wait to learn about the unknown." Congratulations, Cody. You're getting a Planetary Radio t-shirt from ChopShopStore.com, where the Planetary Society has its store, and Bruce is modeling it for me right now. You'll just have to imagine how stunning it actually looks like.
Oh my.
I got more. Devin O'Rourke in Colorado knew how to get to us. Sirius A, although you and Bruce are pretty big stars to me. I think we're within 10 light years. Bert Caldwell in New York. Our son, Sol, would be in 4th place, with Alpha Centauri A in 2nd and Sirius B in 3rd. Several people, not a lot, but a few, mentioned the sun. But you did say the biggest star within 10
and then
light years.
continue straight on.
You did just fine.
Actually, I said the most massive star.
Okay.
Go straight
That's
on.
Better. Matthew Easton in Virginia gave us a long list with Wolf 359 at 11th place. Wolf 359 is, I guess, is going to have to wait until the year 2367 to become known for anything important. This is a gift for you Trekkies out there. Zimmer in Germany obviously is reading Andy Weir's Project Hail Mary. He says, all in all, a nice star, but like so many in the neighborhood, it will soon be infected by astrophage, which will significantly bring down the real estate value. You have to read it. You got to read it. Thomas Pugh in Virginia. I seriously had a rough time finding the answer to this one. I had to hound my computer for the answer, but in the end, it was a doggone good star. I give it a solid A.
Well, I'm wagging my tail at that one.
I thought you'd like that one. Hey, in the Space Poetry Corner this week, a first-time entry from very long-time Planetary Radio listener Homer, who lives in Ionia, Greece. Sirius rises late in the dark on summer nights, star of stars, Orion's dog they call it, brightest of all, but an evil portent, bringing heat and fevers to suffering humanity. Okay, that excerpt is from the Iliad. It was actually submitted by the very much alive Christopher Beck, also in Virginia. Virginia, well represented. But we went classical for the poem this week.
Yeah, and it got really dark in a hurry. I guess that's what makes it a classic.
Star Trek and
Turn
Greek
left.
classics in one What's Up segment. We're ready to go on to another contest.
I'll try not to add any more popular or classical culture while I do this, but you never know. So as of now, June 2021, how many of the 9 spacecraft that have visited Jupiter are still communicating with Earth? We've had flybys, we've had a couple orbiters. Technically, if one dropped a probe, you could consider that 10. But of these spacecraft that have visited Jupiter, how many are still communicating with Earth as of now? Go to planetary.org/radio contest.
I think I could do this one. I might enter. You have, and so do I.
I keep telling you you're not eligible.
Oh, yeah. All right. You have until Wednesday, January 9th at 8 a.m. Pacific time to get us the answer and win yourself one of those aforementioned Planetary Radio t-shirts. That's it. We're done.
All right, everybody, go out there, look up in the night sky, and think about why Matt keeps getting the trivia contest wrong every time he enters. Thank you, and good night.
I'm never giving up. It's only been 4 shows? I'm never giving up. He's Bruce Betts, the chief scientist of the Planetary Society, who joins us every week here for What's Up. You're listening to some of the beautiful music created by Vangelis for Scott Bolton and the Juno mission. Imagine that you are descending through clouds.
carried on. You have arrived at your destination.